All right, welcome everybody to the second co-class. Let's see what weird going on here. 1 second. So, hope you're all doing well. I want to encourage all of you to talk if you want to. I noticed after classes on Monday that I'm starting to go a little bit hoarse, so I need to make sure to talk less, which you will all help me do if you talk more. So actually saying words would be great. You're also welcome to use the chat. You're welcome to turn your video. I would love to see your faces, but again, if you don't want to share your face with the world, I totally understand. But I'm just sitting here looking at myself, which I mean, it's fine, but I also am looking at all your photo roster photos, so I can kind of try to associate a face to a name. So if you wanted me to look at a different face, you might want to put the picture up here. Let's see, what else did I want to say? First off, are there any questions about things in general? About either Canvas or the YouTube videos or Gradescope, I guess. I'm going to try and pause a bit when I ask questions to give you guys a chance to answer. I know it can be sometimes intimidating to want to speak up in class with everybody else, but really, you're welcome and encouraged to do so. So there was a couple kind of businessy things I wanted to go over before we started maybe talking about some math. So first of all, I learned how to share my screen finally. Well, it's not that I didn't know how, but I fixed my settings so that I could share my screen. Yes, so good. There's a question I see, Genevieve. The first quiz will be on Monday, and I will post it up on Monday morning. You can all access it. I did also on Canvas. I posted an announcement about a couple different apps you could use to scan your quiz. I have found Genius Scan to be particularly good at scanning things and emailing them to myself. Harold, yes, we do have a quiz. It's on Monday. The quiz is really for your own benefit. If you take the quiz, you will get full credit. I will grade it and give it back to you with comments so that you can see the things you've done correctly and the things you've done incorrectly. But it's a full participation points quiz. Once you do it, you get all the credit. I would like you to do your best so that you can kind of gauge how you're understanding the material so far. But yeah, that's the whole point of the quiz, just to kind of see where you're at. Let's see. There was something. Oh yeah, so I was saying, as far as taking the quiz, I'm going to upload a PDF to Gradescope you'll be able to access, and then you can either, if you have a printer, print it out, write your answers on it, and scan it back using Genius Scan, or there's a couple others. I found Genius Scan to be the easiest one to use that was free and seemed like it was, I could just email myself the documents really easily, or put them in some file on my computer. That's what I want to do. I want to fix this. Sorry. I don't like not seeing the top of my head. What else? Yeah, so that's how you'll do that. There was something else I feel like I wanted to say about Canvas. Where'd you go, Canvas? Nope, none of those are Canvas. I did watch Sanders' video yesterday, which was perfectly fine, although I felt like he maybe talked about a lot of things that while they're important, they're not all that vital to the class. So he talked about codomain, which is kind of like the range. I wouldn't worry about codomain, like just think about range, forget about codomain, unless he makes a really big point of it later on, but I don't think he will. Sorry, 1 second here. There was something else I wanted to say about, I wanted to ask you guys about YouTube. So for the YouTube videos, those of you that have watched any of them, I'm imagining you can only watch them by clicking on the link from Canvas. Is that true? Would you give me a yes or a no? Yes, no. Remember, you can find the feedback things in the manage participants area. I see a yes. So great. Yes, I forgot my question. I think the question was you can only watch them by clicking on the links, right? Which seems like it might not be the best. Like if I were over on YouTube, I would kind of hate to have to go back and forth to Canvas to see the different videos that are posted. So I'm thinking I might change the YouTube permissions so you can just kind of see all the videos there. The videos are categorized by class. So I'm going to show you my screen for a second. Let's see, where's the YouTubes here? There we go. So, sorry, 1 second. Where's my stuff? So, okay, sharing my screen. Yeah, okay. Sorry, I have to, 1 second. Sorry, it takes a moment here. I have to do this every time. It's annoying. Okay, okay. Let me write myself a note. Sorry, screen sharing. I think I have to do something later, but I think for now it'll be fine. Okay, cool. So you can all see my screen now, and you can see I'm on my YouTube page, although you might not be able to see my YouTube page like this. So if you look at the page here, you can see kind of all the videos. I've done videos for stats and other classes, but you can, on the left here, if you look at the show more. So when I enabled YouTube, I think you should be able to go look and just see the Math 17A videos, and that'll show you all the videos I posted for the class. I think that might be an easier way for you guys to access things. So I'll go change the permissions on the videos. In fact, I can even probably do that. I'll do that later. To public so that you can all kind of see them right off the bat. All right, let me stop sharing here. So let me ask, do you guys have any questions about the math you have seen so far? Or any topics you would like me to talk about today? If you want, you can use your words. Has Sanders given you guys any homework yet? Okay. All right. So he's giving you one lecture. He's posting another lecture later today. And no homework yet. I guess that means we should just kind of do some stuff. All right. Problem is it's hard to know exactly where things are going to go because people do things so differently in this class sometimes. Sorry, I'm just kind of contemplating exactly what I want to do here. Let's look at this. Sure. Okay. We will. I think. Sure. We can definitely talk about that, Gabriella. So I did do 1 or 2 examples of the composite domain. So the fog domain, or F of G, or F composed with G domain questions. I can certainly do a couple examples like that. There are also 1 or 2 examples already on YouTube. So let's see here. Yeah, I think I prefer the whiteboard. Document camera's all right. I might use it at some point. But let's go ahead and do this. Also, no, we're fine. Yeah. Sorry, so to make sure. So I know last time the recording from the class was kind of funky because my video wasn't pinned. My video is pinned now, right? Yeah, my video is pinned, so it should look fine when you see, if you want to watch the video on YouTube later. So let's go ahead and talk about some domains. So we often don't just ask about the domain of a composition like he was doing in class. So for example, let me move my chair out of the way here. And you guys will let me know if my volume is not great. I assume it is. This microphone does a pretty good job of picking up everything. So also, if you have questions, feel free to unmute yourself and say them because I might not see you if you are trying to type something in the chat on right on the board. So let's look at this example. Let's say our function f of x is, let's make it not too terrible. Let's say f of x is 1 over x, and g of x is 3 over x minus 2. Okay. And we're going to look at both directions so that you kind of get to think about both things. So first of all, when I look at each of these, I kind of automatically think about what the domain is. Here, we're pretty clear that x can't be 0. Here, we're pretty clear that x can't be 2. If we were being more, right, if we were kind of being really specific or rigorous, we might say for each of these separate functions, right, we might make the interval notation. So we might say here that the domain is everything from -infinity to 0 exclusive, along with everything from 0 to infinity. This just means all the numbers less than 0. This just means all the numbers bigger than 0, but we don't actually get 0 using parenthesis. Same deal here. The domain would be -infinity to 2 exclusive, and then 2 to infinity. Everything less than 2, everything bigger than 2. All right, so I want to look at the composition. So some people use this notation, f circle g of x. Most people prefer this notation, f of g of x. Either way is fine. Let me do one thing here. Yeah. I'm getting the glare off the screen there. So if we look at this, f of g of x, well, f of x is 1 over x, g of x is 3 over x minus 2. So f of g of x is f of 3 over x minus 2. And then that's 1 over 3 over x minus 2. Now, if you leave it like this, it's really obvious that 2 is still not in the domain because we can't divide by 2. Let me do one thing here, sorry. Big old forehead right there for it, but okay. But we often like to simplify this, right? When you have a fraction, or like when you have a fraction in the denominator, we usually like to flip and multiply it. It says 1 times x minus 2 over 3, which is x minus 2 over 3. And if you just said this was f of g of x, you might lose the fact that 2 actually isn't in the domain. So I think he was doing a class where he said, if you're going to say f of g of x was this, you'd have to write f of g of x is equal to x minus 2 over 3, but x is not allowed to be 2. Right? Because it's, although it's what's called, it's the, there's a word that I can't remember right now. Anyway, we have to specify that 2 isn't in the domain because it's not allowed to be there. And what I always like to say, what I always remember when I'm doing a composition of functions, is we have to always obey the domain of the inner function for sure. So this inner function g of x, x equal to 2 was excluded. That's automatically going to have to be true no matter what simplification we do afterwards. There might be other things that also get excluded, but for sure 2 is going to have to get excluded. So let's look at the other direction. Let me loosen the board a little bit. Let me make sure this is just it. All right, what is it? I'm going to go back one next time, actually. Okay, so let's say I want to look at g of f of x, which is g of 1 over x. Right there, before I do anything else, I make myself a mental note. Oh, I know x can't be 0. no matter what happens next. And then g was, what was it? It was 3 over x minus 2. So it's 3 over that minus 2. Now again, if you left it like this, it would be really clear that 0 wasn't in the domain. But most of the time, we don't like fractions and fractions. So a lot of people would simplify this to, let's see, if I was going to simplify this, the easiest would probably be to multiply by x over x to get rid of the denominator in the denominator. So I'm going to get 3x over x times 1 over x is 1. X times negative 2 is negative 2x. Now, the way he was doing this in his lecture was he was saying, okay, here's my function, g of f of x equal to 3x over 1 minus 2x. X is not allowed to be 0. There's also another number that's not in the domain, right? If you look at this denominator, 1 minus 2x, and we set that equal to 0, we get 1 equal to 2x. We get x equal to 1/2. 1/2 is also not in the domain of this function, but he didn't feel like it was necessary to state it in this kind of problem, because if we look at this, we know it's not in the domain. Now, depending on what you're doing, that's fine. If I was asked what's the domain of g of f of x, I would say the domain is everything except for 0 and 1/2. Right? We also can't have x equal to 1/2. So I would say the domain is everything from negative infinity to 0, union 0 to 1/2, union 1/2 to infinity. That's how we write the domain for this. Yeah. I think that seems pretty good. Should I do another example? I'm happy to. What? Might have to make like have to change some participation guidelines to say you have to talk during class. Tighten my word. They're making me too loose. Sorry, one second. I guess that'd be one advantage of the document scanner. They can just use paper. Well, that's kind of a waste of paper. So. I think I do know what I want to do next, though. I know, like, I think. Never mind. Come on. Let's look at one. Oh yeah, here. So here's kind of an interesting example. So what if f of x was x squared and g of x was the square root of x? And I wanted to look at the domain of f of g of x and g of x. So for f of g of x, it's equal to f of the square root of x. So already, and how's that pen look, by the way? Sure, we can talk about codomain. It's, yeah. Can you guys see this all right? I feel like I can't see it very well on the screen. That's all right, I guess. So if we look at this, it's going to be the square root of x quantity squared, which is just x. But if we think about this inner function, that the inner domain, the function, the domain of the inner function is that x has to be greater than or equal to 0, right? So we've got a square root of x here. So this function, if we graphed it, here's what the graph of f of g of x would look like. It would look like y equal to x, but just starting right there. On the other hand, if we look at g of f of x, which is g of x squared, which is the square root of x squared, the domain is everything here, right? Because the, well, not just because the inner function has all domain, but because if you look at this, x can still be anything. Now, what's the square root of x squared equal to? Any volunteers? You can even type it. You can also say it. Square root of x squared is equal to, that's a good guess. It's mostly right. It's actually equal to this. Oops, can I type things? Sure. Totally, right. It's actually the absolute value of x, which is interesting. So the domain would be everything. And the range would be just the positive value. I should say the non-negative values. 0 equals to infinity. I can definitely explain why for sure. So let me graph it first. So it looks like this, right? So my explanation of this is usually through example. So if I have a function, let's call it, h of x equal to the square root of x squared. This function does the same thing the absolute value function does, right? For an absolute value function, if you input a number, if it's positive, it gives you back the same number. If it's negative, it gives you back the corresponding positive number. So for example, I know that the absolute value of 6 is equal to 6. The absolute value of negative 6 is equal to also 6. And actually the way we do it is we say it's negative 6, which is 6. And then we take the absolute value of a negative number, you make it positive by taking the negative of the negative. The same thing happens here. If I look at h of 6, well, I get the square root of 6 squared. What's 6 squared? 36. What's the square root of 36? It's not a trick question. Yeah, definitely 6. All right, I'm going to ask you guys to start trying to be more brave and say words. Okay, so now if I look at h of negative 6, I get the square root of negative 6 squared. Negative 6 squared is still 36. And the square root of 36 is? 6. Exactly. Thank you for your bravery. Right? So it does exactly what the absolute value function does. If you input something positive, you get the same positive number out. If you input something negative, you get the corresponding positive number out. So this is the long story answer to the question, why do you get a plus or minus when you're solving the square equation? Like if I was solving the equation, x squared equal to 25, we know the solutions are positive 5 and negative 5, right? 5 squared is 25, negative 5 squared is 25. And usually our process for doing this is just saying, we usually jump down to the final answer, which is, oh, x equals plus or minus the square root of 25, which is x equal to plus or minus 5. But there's actually a few steps that we are allowed to skip, but the steps are the following. You take the square root of both sides, and the square root of x squared isn't x, it's the absolute value of x. So the absolute value of x equals the square root of 25, which is 5. And then the absolute value of x equal to 5 means x can equal plus 5 or minus 5. That's really what we're doing when we square root both sides of an equation. Is we're getting this absolute value of x, and we're getting the positive and the negative answer. So there was a question about codomain, or to explain codomain. And actually, I feel like I should kind of, let me look back for 1 second. So I want to make sure I kind of don't contradict something he has said. So I've got his little lecture up here real quick. 1 second here. Where'd you go? So I've got so many things. There it is. So look at his lecture. Can I look at his lecture? Sure. He says some stuff.
Hello, everyone.
Can you hear?
Welcome to
I assume you can hear him talking on my computer. And why wouldn't you? You can just go into the microphone. Let me turn this. There we go. What did you say about codomain? Sorry. My real answer is you should ignore codomain. But yeah. So codomain is weird. In fact, maybe we should listen to what he has to say. So I'm going to turn this line back on here.
What we call that set the domain.
So,
and that gets associated with a unique element of another set, B, called the codomain. So you can think of a function as being a kind of abstract machine.
Sure. Okay. So, sorry. Yeah. So you've got a function that goes from A to B. I mean, this is kind of not notation we're going to use a lot in this class, but it is somewhat standard math notation. Let me open my window here. It's a little warm. So, the place you start with the domain, the place you end up is the codomain. So for example, the function f of x equal to x cubed minus 2 has a domain, all real numbers, has codomain, all real numbers. Now he goes on to talk about kind of the difference between the codomain and the range.
Object from the domain on a conveyor belt and it rolls into some box.
Yeah.
And out of the box comes another object, and that is the object that it is associated with. So it's a sort of an abstract machine for producing new objects from those ones.
Sorry. Okay, sure.
So the range of f is the set of all y in the codomain, such that y equals f of x for some x.
Okay, that actually was what I wanted to hear. So the range is the set of things that you get to that are in the codomain. So for us, for this class, the codomain is just a set of all real numbers. So all the functions that we deal with are real valued functions where you're inputting something and you're outputting something. So if I was looking at, say, the function 1 over x minus 3, the domain is clearly all the real numbers, all the real numbers except for 3. And I believe he also mentioned that this is called the implicit domain, right? Because you don't have to say explicitly that x can't be 3. The function already kind of limits us to x not being able to be 3. Or there are some other functions where we talk about an explicit domain, where you specifically say, no, I want x to be larger than 0, or I want x to be less than 5, because we've just decided that we're going to limit ourselves in that way. I kind of think of that as an artificial domain, whereas this is the natural domain for this function, right? X can be anything except x can't be 3. A lot of our examples in this class will have an artificial or explicit domain of x or t being greater than or equal to 0, because time starts at 0 and then moves forward. This function has a codomain That is all real numbers. Because that is, I kind of think of the codomain as the target space. Like all of our inputs are going to give us outputs that are real numbers. The range is the subset of the codomain that is all the real numbers that we actually get to. In this function, you get everything except for one thing. Sorry, one thing. You don't get the number 0. So the range here, you can either write it as negative infinity to 0 union 0 to infinity, or you could write it in a lazier way, which is the set of all real numbers minus the set containing just 0. This backslash here is a set minus. Some people actually use a regular minus sign, but that's fine. It just is not what I was taught to do. But this is another way you can write that set. So again, what I'll say about codomain is with rare exception, all of our functions are going to have a codomain that's just the real numbers. And you shouldn't sweat it because I really don't think it's going to come up too much more. You should focus more on the range of a function. That's what's actually important. The range for sure. So you're right. I kind of said what the range was here. So let's actually talk about it. So for this function, f of x equal to 1 over x minus 3. The range is the set of all y values you can get. So basically, I'm going to set this equal to y, and I'm going to try and solve for y and see what y is allowed to be. Or sorry, solve for x. So I've got y equal to 1 over x minus 3. Now, there's a number of ways to do this. You can find the range by finding the inverse function, but that's not something we've talked about really yet. So if I try and solve for x here, which is kind of like finding the inverse function, I multiply both sides by x minus 3, divide both sides by y, add 3 to both sides. If I look at this, what's the only thing y isn't allowed to be? Yeah, we don't get 0. So 0 is not in the range. There's no way that this function, 1 over x minus 3, can ever equal 0, right? There's no value of x that's going to get me 0. But and y is allowed to be anything else, right? So for whatever, like if you wanted y to be 2, well, to get y equal to 2 in this expression here, x would have had to be 1/2 plus 3. So if x was 3.5 or 7 halves, then y would be 2. And for any other non-zero value in this example, that you want to pick for y, there's always an x that will get you there. So that's the idea of what it means for a number to be in the range. There has to be some number in the domain that the function will take to the same value in the range. Sorry, not the same value, to the desired value in the range. So the range is the set of all values that get mapped to, is often the way we say that. Let's look at another example. I'm trying to. I think it's too tight. I want to go this way. Sorry. Go this way. Yeah, off. Good. All right, cool. Okay. Yeah. See here. The problem with the range is sometimes it's not so easy to just solve for x in terms of y. For example, if y was equal to x squared minus 6x plus 5, finding the range of the way I just described, although possible, is not really what we want it to. You certainly could. So first of all, I should say, what's the domain? Well, clearly the domain is everything, right? There's no values of x that make this undefined anyway. So I should say the implicit domain, or the natural domain, is everything from negative to infinity. You could make it different if you said, I want to start at x being greater than or equal to 1, but we're not. The range here, well, let me walk you through the hard way to do it, and then I'll mention the easy way. So you could totally solve for x here because this is quadratic. You can complete the square. I don't feel like I see this green pen very well. I'm using different color. So you can say, okay, well, it's gonna be y equal to, let's see, x squared minus 6x. What do I have to add on to complete the square? What nice square number? Everybody. Less than 10. It's bigger than 7. Yeah, it's 9. Right? Because you take half of negative 6, which is negative 3, and then you square it. Red and blue are the best. Okay, good to know. Although I haven't used black yet. Black's probably pretty good too. So, right, the reason I'm adding on 9 here to complete the square is that then this part here will be x minus 3 quantity squared. But I also have to then subtract 9 and still have the plus 5. Right, so that's the same equation, just with looking a little different. So then I rewrite this as, this part here is going to be x minus 3 squared. Right, this here is always just half of whatever that was there. Minus 9 plus 5 is minus 4. And now I can solve for x. So I'm going to add 4. So y plus 4 equals x minus 3 squared. And then here's where things are going to get tricky. I'm going to square root both sides. So x minus 3 is equal to, well, in fact, really, I should do this. I should say that, sure. X minus 3 squared square root is equal to the square root of y plus 4. I'm getting a little bit too in my head here about this. So here's what I've got x minus 3 equal to the square root of y plus 4. It's really a plus or minus square root of y plus 4. And then you can solve for x. Again, the idea isn't so much that we care exactly what x is that we care how y gets restricted. Here we see that, oh, y plus 4 has to be greater than or equal to 0. So y has to be greater than or equal to negative 4. So that's one way you can see. This is definitely the hard way to see the range here. There's a much easier way to see the range. But I wanted to point out that this is an option. If you can solve for x, then you can say, oh, well, what is y allowed to be? And here, y is allowed to be anything bigger than or equal to negative 4. But it can't be like negative 7, because negative 7 would give us a negative 10 square root. Now, here's the way easier way. This is a parabola. We know how to find the bottom of a parabola. Find the vertex. The x-coordinate of the vertex is negative b over 2a, which is negative 6 over 2 times 1, which is 3. And the y-coordinate of the vertex, you plug in 3, you get 3 squared minus 6 times 3 plus 5, which is 9 minus 18 is negative 9 plus 5 is negative 4. And let me ask you guys, does this parabola open upwards or downwards?
Upward.
Nobody knows?
Upward.
You want to say anything? All right, well, it's y equal to positive x squared minus 6x plus 5. This coefficient being positive means it's an upward opening parabola. So my parabola, which I've kind of run out of space to draw, I'm going to draw it over here just a little bit, has a vertex at 3, negative 4, which is somewhere down here, 3, negative 4, and then it opens up. So you can see, oh, look, the lowest y value is negative 4. So the range goes as low as negative 4, and then up as large as you want. So y being greater than negative 4, or we can say that the range is negative 4 inclusive, right? Because it's greater than or equal to negative 4. So we use the bracket, and then it just gets bigger and bigger and bigger without bound. Most of the time when we're finding range we're probably doing it graphically or using this kind of process. Really, this is kind of just a different version of using the inverse function process, right? If you've learned, well, might as well just say it. So this is kind of the same as saying the following then. Which is that if a function is invertible, so if f of x is invertible, meaning it has an inverse function. Whoops, that's not how you spell inverse. There's no f in inverse. Which we call f inverse of x. So if your function is invertible, then here are some things that are true. The domain of f is the same as the range of f inverse. And the range of f is the same as the domain of f inverse. And the reason this is true is because when you find an inverse function, so again, I should back up a tiny bit. For a function to be invertible, it has to be one-to-one, or pass the horizontal line test. So just a couple quick examples and we'll come back to this. Red. So y equal to x cubed, totally invertible. Passes the horizontal line test, right? It looks like this, kind of, right? Any horizontal line you draw goes through only one point at most. So definitely is invertible. And the inverse, if we switch x and y, you get x equal to y cubed, and then you solve for y, you get y equal to the cube root of x. The inverse looks like this. Kind of like that. And it actually literally looks like, if the drawing was better, it looks like you took this function, y equals x cubed, and flipped it across the line, y equals x, to get y equal to the cube root of x. These functions are inverses. On the other hand, not this one, blue. Here we go. Not this one. Oh, well, here's another one. Oh, there it is. On the other hand, if you were looking at, say, y equals x squared, y equals x squared is not invertible. It does not pass the horizontal line test. I can draw a horizontal line and go through 2 points. If you switch x and y, you get x equal to y squared. So the reason this isn't invertible is because when you switch x and y, you get something that's not a function. Right? If a function doesn't pass the horizontal line test, the what's the word I'm looking for? The equation you get when you interchange x and y isn't going to be a function because it won't pass the vertical line test. Because again, you're flipping this across the line y equals x, and when you flip across the line y equals x, things that were horizontal lines become vertical lines. So not passing the horizontal line test here means that this other thing doesn't pass the vertical line test here, which means it's not a function, which means it's not invertible. So to be invertible, you have to be one-to-one. If you're invertible, your domain and your range, the domain of f is equal to the range of f inverse and vice versa. The range of f is equal to the domain of f inverse. And the reason is exactly because you're switching the x and the y, right? The domain of f is all the things x is allowed to be. The range of f is all the things y is allowed to be. So if you're switching x and y to get f inverse, then all the x things here are all the y things here. In fact, that would be a good thing to write, James. X things here are the same as the y things here, and vice versa. The y things here are the same as the x things here. And again, I just want to emphasize this one more time. Because you're switching x and y, that's why the y things here are the same as the x things here, vice versa. And that's exactly where I'm headed. How do you find, how do you not tighten this board too much? Let me go back, sorry. Let me kill this board. Break it. There we go. So, how do you find an inverse function? Well, we actually that's what we were kind of doing in those previous problems when I was solving for x. It's just usually people, in fact, this one here, I hadn't erased already. I mean, it's not really invertible. We kind of found it anyway. Yeah, it involves solving the equation the other way. Usually we just switch x and y before we do it. So let me give you, we got not a lot of time here. So let me give you actually a kind of challenging example just because it's one you might see. So let's say our function was, yeah, sure, 3x minus 2 over x minus plus 4. And notably, the domain here is everything except for -4. The range, I don't know, but we're going to find it. So how do you find the inverse? First, a non-step. I'm going to use y as the f of x. It's just easier. Second, switch x and y, which is also pretty easy. So you should only be one y, it'll become x. There might be multiple x's, they all become y's. That's a 4, not a 2, sorry. There. 2 minus 2 becomes 4. And then you're going to solve, and the next step is actually the hard step, then you're going to solve for y. So in this case, I'm going to have to multiply both sides by y plus 4. So I'm going to get x times y plus 4 equal to 3y minus 2 over y plus 4 times y plus 4. The whole reason we multiply by y plus 4 was so that the y plus 4 in the denominator here will cancel out. Right? We don't want to deal with denominators, we don't have to. Then we distribute the x here. So you get x times y plus x times 4, which I'm going to write as 4x equals 3y minus 2. We're trying to solve for y, right? We had x equal to something with y's in it. We want y equal to something with x's in it. So bring all the y's to the same side. So xy minus 3y. Bring all the x's to the same side. Negative 4x minus 2. Factor out a y. Y times x minus 3 equals negative 4x minus 2. And then finally divide by x minus 3 to get y equal to negative 4x minus 2 over x minus 3. So let me ask you guys, what's not in the domain of this function? What one value isn't in the domain here? Yeah, exactly. So here's my inverse function. F inverse of x is negative, whoops, let's see, we're supposed to more than here. Negative 4x minus 2 over x minus 3. So 3 isn't in the domain of f inverse, which means 3 isn't in the range of the original function. So f of x equal to 3x minus 2 over x plus 4 has a range that consists of everything except for y equal to 3. So it's everything from negative infinity to 3 exclusive, union 3 to infinity. Which also might be semi-obvious to you, maybe, if you recognize that 3 is the horizontal asymptote of this function. So, I think we're actually about out of time. I'm going to try and make, so I should say, I don't have a whole lot of ideas yet for what I might try to do this afternoon for you guys, as far as making some videos. I do have to make some videos from my other classes yesterday because I had some computer issues. I had to back up my computer to a couple hours previously because I deleted a bunch of files accidentally. So fortunately, everything worked out. My computer is good and working, but I wasn't able to make any videos from my other classes. So if there's anything you want to see, let me know. I'll try and look at Sanders' lecture this afternoon and see if he does anything that seems like I should address it. But definitely send me an email or post a discussion thread, which is worth a participation point. And limits, yeah, we talked about limits for sure. I'll do some limit examples. But yeah, let me know. I'm going to end the meeting because I have another meeting I have to go to in a few minutes. But send me an email, or I'll do limits, or the other thing. Discussion thread. Yeah. All right. I'll see you guys on Friday. Bye. You're welcome. Good seeing you. Thank you for having your video up. I appreciate it. Ending the meeting.